Yes, thank you again for joining us here today. Our next speaker is Professor Thomas Brox. He's absolutely one of the great leaders in the field of computer vision today. He received his PhD in computer science from the Saarland University in 2005. Has been a postdoc at the University of Bonn, the University of Dresden, and the University of California. Since 2010, he's heading the computer vision group in Freiburg. Thomas has put his name on many well-established practices in the field of vision, such as optical flow estimation and object segmentation. At the same time, he is very much involved with recent advances in the field, such as convolutional networks for flow estimation, image segmentation, image generation, and many more. So please join me in welcoming Professor Brox with a round of applause.
So, sounds better. Okay, good. So, welcome everyone. Yeah, deep learning has served us well in the last few years. Whole industry has been built around that. Yeah, people are also earning good money with that. PhD students are hired away from university directly after their PhD or even earlier. So, yeah, so deep learning is a success story, but at the same time, we must admit that we are not completely happy with the way on how deep learning is solving the tasks. I mean, it's good for a couple of tasks that that are well defined and where you can put labels and then you can learn these labels at the same task. But the kind of learning is actually still different from human learning, and where humans are much more generally applicable. Yeah, so you learn one task, you can also learn another task, and you can also exchange knowledge between the tasks. And that's not the case with this current label-based learning that we see mostly. And that comes with problems. So the most important problem that has been observed in recent years is that when you run out of the training distribution, then things don't go well anymore. Then you actually lost. You can be lucky and it still works in some case. And also in talks with scientists, you often hear this, it works or it doesn't work, but people cannot say why it works or why it does not work. and that's also a sign that when you run out of distribution, you actually have absolutely no guarantee that anything is working. You can be lucky and you can write papers with nice numbers somewhere, but it's actually not a trustworthy result that you would get. And to humans, we can rely on moving to another task that is a little bit different, much more. And the reason for that is maybe that the kind of learning is different. It's much more self-supervised. So that means the training loss, not sure how the training loss looks for humans, but at least the training loss that we would need here for computer vision and for machine learning is something that is also a bit more generic and is not so task-specific based on these labels, because that makes it likely that you learn some shortcuts that are good for the training task and just make the training task be solvable, but won't help in a new task that is slightly different. And you see that, for example, when you, or in car companies, train on US roads and then they want to employ their cars in Europe, well, that might go bad. Yeah, so the street signs might look a little bit different. Every human would recognize them as the same one, but they are different. And also the roads look a little bit different. The greenery might be a bit different. Yeah, all these little details can be a problem for these autonomous cars, and that's why that's actually a big topic, and a lot of money is invested in transferring the things that you have already learned to another domain, and there are specialized techniques that can do that, are also quite successful, but again, these techniques don't generalize. Yeah, so if you then try to solve another problem again, another transfer problem, then it's again different. You need to tweak your new transfer method for that. Another example is you train on rendered data. because for that you have your annotation for free and you can easily generate large amounts of that. But then you want to employ your method, of course, in the real world, on real world data. So that's also a nice transfer task. And in the beginning, people have thought, yeah, now we have solved the problem and we can just create synthetic data of our tasks and then we can just solve all the problems. But the problem is that this transfer is hard and it doesn't work reliably. That's another instantiation of that. And if you want to extend the number of classes, for example, then you're in this few-shot learning setting. So yeah, when humans, if you show them an image of a new object, then they just need this one image or maybe from two viewpoints and then they can recognize this image. That's not true for machines. Yeah, so sometimes it works, sometimes not. So all this few-shot learning is not as good as if you would have thousands of training samples again. And also just if you look at the curve, so how the things change. Yeah, so of course, if you see three images of 4, 5, then you might get a bit better, but then it saturates. And for machines, it actually saturates when you see 1 million images or so. That's just unreasonable. So there you see that all this generalization doesn't work super well yet. And as I said already, so with self-supervised learning, that's a bit more promising because these shortcuts during the training task are less likely. Yeah, a self-supervised task is by definition often something generic, and that means the features that you will learn, they are less specific to the task, which makes it harder to learn the task actually, but it's more likely that you learn something that you can also reuse somewhere else. And that has also been a recent trend in the last 2 years to push more and more this self-supervised learning. Before I go into this, I want to move on to, or I want to start with a task that actually allows for open world generalization. And that is optical flow estimation. So when we started this FlowNet, then we trained that with this flying chairs data set. So it's a very silly data set. You just take some flicker images, you apply some affine transformations to them, then you do the same for some chairs and you paste them randomly into the image and you move them in the next image. That's a very simple generated data. And if you now train with that, you could think, okay, it works for these kinds of chairs, but it doesn't work on new image data, but that's not true. Yeah, so for optical flow, it generalizes actually to completely new data. You don't need to fine tune anything with real world data. You can just train on the synthetic data and you can use it on real world data. Yeah, so we extended that a little bit with this flying things data set, but also that is a procedurally generated data set. It's 3D, so you can really also argue about 3D space and compute depth. But it's still, you're just randomly pasting objects 3D objects into a scene and get the ground truth optical flow from that. Yeah, and on test data, I mean, the first one is now, the first one is now a chair. Of course, this works. Yeah, we've trained it with chairs, but it actually doesn't matter whether it's a chair or a car or whatever. Yeah, so it can generalize to new data. Yeah, and that's very different from all these recognition tasks that you see. So if you do the same with recognition tasks, you generate some synthetic data, render data with the class labels, and then you try to apply that on real world images, it won't work at all. So you actually need always some fine tuning step afterwards. Of course, the same thing also applies for stereo, because stereo is a very, it's actually a special case of optical flow. So also here you can train on these flying chairs, flying things data set, and then you can use it, for example, for bushes. Yeah, so depth estimation on bushes, and then you can do bush trimming with that. Yeah, so that was an EU project we had with some other partners where we wanted to build a robot that can trim bushes. Yeah, and this shows completely synthetic training, and you can apply it on real world data. So that's what we would like to have also on other tasks. So why is image classification different from that? And the first difference that we will see is that optical flow and stereo are correspondence tasks. So that means you don't want to learn a feature that represents something particular, but you just want to have features that allow you to match between two images. Yeah, the features that are good for matching, they are good features for the task. And already during training, you're applying this loss that you want to match different structures between two images successfully on various images. Yeah, so already the loss is actually a very generic loss that is not bound to any classes or so that you see during training. And that's a big difference. Of course, there are also some priors that you learn. For example, when there are occlusions in the scene, then you cannot do a matching at those positions. So you have to learn how the optical flow must look like in this occlusion area. So this is the prior that you have to learn, and it depends, of course, a little bit on the scene, or at least you can do it better when you know something about the scene. So this is prior knowledge that is scene dependent, and there you benefit from some fine tuning in the particular domain. But on the other hand, it also has some generic thing that you can learn here, because the occlusion itself is a concept that you can also learn from just a box that is being moved over the image. You already have occlusion phenomena there, and you know from which direction, for example, you have to smooth in the optical flow from the background side and not from the foreground side, for example. Yeah, so this concept can already be learned from the synthetic data. Yeah, so there's a little bit of prior that is scene specific, and that's also what we see as humans. Yeah, so of course we are also not good or perfect on all tasks. Yeah, so if I have an electrician at home, then I hope that he can do the job better than me because he has learned it. Yeah? But I can also do a little bit of this electricity. Yeah? So you see there's some generic knowledge, and then there's some specialized knowledge that you get by fine-tuning or more training on the task. Yeah? And it's the same as what we want to get here when we talk about open world generalization. Now in recognition, you have more these remembering tasks. Yeah, so you want to remember how a certain pattern looked like, and then you find it again in the new image. So the problem here is that you actually have to encode this knowledge that you want to remember, and you don't want to remember everything because that's too much. So you have to abstract information away. And now during your training task, yeah, you just have these training samples, and now you abstract everything away that is not necessary to encode the training samples. It doesn't tell you anything about the test samples, and that is the big problem. Yeah, so the features are now only made for discriminating the training samples. They are not even made for describing the training samples. They just need to be good on discriminating the training samples. Yeah, and that way you actually often throw away very important information that you would need later for generalization, and that's the big problem. And that's what you could at least alleviate a little bit if you don't have these discriminative training tasks based on labels anymore. Okay, so since optical flow worked well, we maybe move into a position in between, where we are between optical flow, where you actually match between two images, and classification, where you try to match very different instances of a class. And in between is actually instance matching. Yeah, so you have the same instance, but you can see it from different viewpoints, and you now want to recognize this same instance. Yeah, so for example, this car. Yeah, so these two different images look very different. Yeah, so from the raw data, they are very different images, but since it's the same instance, you could learn some features that map actually the feature space to the same point for these two images. So the variation that you need to learn is pose, camera parameters. Yes, you might take the picture with a different camera from a different viewpoint. The lighting might be different. The background can be different. So you actually have to focus on the object itself. And there can be occlusion, so you don't see the whole object, but only part of it. Yeah, so these are the variations that you must expect when you talk of instance matching. And the good thing is that much of this can be simulated, at least approximately, via data augmentation. So you can actually synthetically generate these variations, and that means it allows for some self-supervised feature learning. So you don't actually need labeled samples for this, but you just need images that represent the instances, and then you modify these instances, and that way you generate these different views of it. And now you can, like for optical flow, you can learn features that are good for matching, or actually, in this case, not for matching, but for mapping all these features to the same point. And you can also imagine that this might be a general principle that you can learn actually on 5 instances, and it might then also work on a 6th one that you have never seen during training. Yeah, because you're actually learning this this principle of mapping features that come from different viewpoints or different lighting to a common point in the embedding space. So that's nothing that is specific to that instance, but it's actually something generic. And that way, the whole feature representation might generalize. So that's the big advantage here. And what we actually see today in all this self-supervised learning, feature learning, it's actually this principle. Yeah, so you're doing actually learning instance representations, and then you hope that this feature representation is also good for many other things. And it turned out that if you do it right, that's quite true, although we are not perfectly there yet. Just for some history, we already did that in 2014 in a simple fashion. So there it was not some contrastive learning, but it was still an instance discrimination. So we just took a single patch, so that can be an arbitrary image, and then we applied all these transformations that we want to be invariant to that patch, and we did that for many patches, and then we just had a loss that had to discriminate between all these different patches. So you can just regard these patches and with all its transformations as a surrogate class, and then you try to differentiate between them. And that already gave quite good results for that time. Of course, the learning machinery at that time was not as good as it is today. Also, models were much smaller and so on, but the principle was already there. And this is still the principle that we're using today, but in a slightly improved version, where this contrastive learning, where you don't say you want to discriminate samples, but you're saying that you want to have images from the same instance, but different views. You want to map them to the same point in the embedding. And instances that come from somewhere else, they should not be close to that embedding. Although recently it has been found out that actually this contrasting is actually not that relevant. You just need a proper normalization. That's currently still in the making on how that should look like. But in principle, all these negatives, you don't need to carry them around ideally. But for understanding the principle, it's quite useful to see that, okay, you want to map all the things that come from the same instance to one point, and all the others should be pushed away from that. Yeah, and that's what you see in the literature. So contrastive learning fosters this instant matching, but surprisingly, it's also good for classification. So just last year, it has turned out that you can even take these features and do a clustering, and then surprisingly, you actually get almost the classes that are in a data set. Yeah, and now you wonder a little bit, where do the classes come from, although you didn't put any classes in there. Yeah, you just had this instance discrimination. Yeah, you had tons of different cars. They're all looking very different, and now suddenly, although you didn't put that in, they end up in one or two clusters in this embedding space. And so where could that come from? I also, at the beginning, I thought something is wrong with the code. Maybe they used the test data during training or something like that. But yeah, if you think about it a bit more, then you could wonder how different are these instances really. Yeah? So I showed you two examples. So for this, so these are two different cars here. So they are really not the same instance, but very different cars, but they look quite similar from the features. They share a lot of features. Yeah, so it's actually not too hard to have them in the embedding space close by. Huh? Whereas for these airplanes, this is a bad example because they are both airplanes, but they actually don't share much information. Yeah, they have wings, but they look very different. They have a tail, but they don't look very different. You see the wheels for one, for the other ones, they're hidden. Yeah, so not much information to connect the two. So how do they end up in the end in the airplane cluster? Yeah, maybe they won't, but it also happens that things like that end up in the same cluster. And the reason for that is the transitivity in your embedding space. Yeah, so these two samples from that class might be far apart, but since there are many other samples on the way that have something in common with one and the other, they connect the two via transitivity, and that's why in the end they can end up in the same cluster. Yeah, and this contrastive learning actually respects this transitivity, although this is very hard to control, and that's probably all the parameter fiddling that people are doing right now to make that better. But maybe there will be also a principled approach to that. Maybe contrastive learning is not the best way to do it, but the point that you can use this transitivity It's well known in clustering, yeah, so there are different clustering methods. K-means won't respect it, but if you use, for example, a spectral clustering technique, then if things are connected on a path, then they will end up in the same cluster. And with this principle, you can actually come from instance matching, and you still, in the end, have the things concentrated on one point when they belong to one class. And that's probably also how classes actually appeared in the human brain, because things are in the end the same. There are, of course, other cues like functionality and so on that we don't have in vision, but just from the vision alone, you can already connect things, although they don't look very similar on first glance. Yeah, so this explains why the self-supervised learning also works at the class level. Yeah, so I mentioned here this paper from Mathilde Caron, where it is particularly obvious that you can even do segmentation in the images based on these features. And that was kind of surprising to me. There's one caveat here, and that is localization. Yeah, so all these arguments that I just brought would fail if you have multiple objects in the image. And now you do all this self-supervised learning, and then you're actually mixing information from different objects, and that might destroy all the arguments that I just brought. And that might also be the reason why ImageNet is such a popular data set, because if you look at ImageNet, then you see a strong bias here. Mainly there is a single dominant object class in the image. Yeah, so they selected the data actually this way, because otherwise at that time they couldn't label it properly. If there are two different classes in the image, they only had one class labeled per image, so how would they do that? Yeah, so that's why they ignored all the images with multiple objects in there. So that's one thing, and then also the object is typically dominant and in the middle of the image. If you ever wondered why this center crop thing would be of any use and why it is useful, well, it's useful because ImageNet is made this way. Yeah, so then center crop makes a lot of sense because in the center there's the object, and if you can crop it, and then you have a different view of this object. Yeah, and actually Mathilde Caron actually did this multi-crop strategy where she then compares small parts of that object to the big one, and that way you can even learn an embedding where the parts are represented of that object. And this all just works if you can assume that the whole object fills the image more or less. Yeah, so it can be shifted a little bit, so this noise is not so much of a dramatic thing, but if you would not have these dominant objects in the middle, then the whole concept may not work. So I don't have evidence that it won't work. We haven't tried it, the same thing on Coco and then see that it fails, but I would expect it that at least you have much more trouble when you try the same principle on something that is different from the ImageNet style data. Okay, so here's some intermediate summary. So we have seen that instance matching extends to an open world setting, so that you can do. And in particular, it doesn't require supervision. So all these labels that we are used to need, you don't need them anymore. And then we have seen that instance matching plus graph transitivity can actually use as proxies for class level clustering. So although you don't have any class labels, in the end you get something that is quite close to the classes that we as humans would also build. And if the data is already ordered like that, then it also works in practice. Yeah, and at the last point, I stated that if you have a mix of multiple classes in one image, then this could be an issue. So that's why this object-centric bias that you have on ImageNet and also a couple of other data sets is quite helpful. Okay, so this ends my first part, and I want to move now to something that might be even more powerful and that has also been quite popular in recent years, or has become popular in the last 2 years, and that is the use of image-text pairing. Yeah, so if you not just have images, but you have an image with corresponding text, then you actually have some extra information that is almost like labeling. It's even better than labeling. Yeah, it might be more noisy, but it has much more information. Yeah, so with these labels, it's always a bit ambiguous what label exactly you have to assign to a particular image, because the image shows multiple things and not just this one label. But if you have a text, then you can express much richer things. Yeah, and a good thing of image text pairing is that often you get it for free. So many images, especially in the internet, actually come together with a caption or some text attached to it. For example, if you search for a product on Amazon, you're actually typing in that you now want to have a bicycle. Yeah, and then you type it in, you get tons of images of bicycles. Yeah, so and you get actually not only the images of the bicycle, but actually what you get is the product description. So it describes exactly what bicycle, which color, and so on. And all this information comes together with a couple of images. Often the images are actually not as good as the text. Yeah? So that's one example. Or another example is that you can have videos and use the subtitles. Yeah? So often the subtitles are not that good because they write what the people are saying, and that does not necessarily correlate to what you see. What's much better is these audio descriptions for visually impaired people. So some of the movies that you find, they actually have this audio description available, and that's very, very good video text pairing, because for that they describe exactly what you see in the video, at least the most relevant parts of it that fit into that time window. Yeah, so you get a couple of video text pairings, and here's an example of paired image and text. So in Google, you type some description. Yeah, so here the image of a dog on a red skateboard, and then you get lots of images. And if you look at it, it's really the dog on a red skateboard. Yeah, and you can of course now generate lots of these text descriptions, put them into Google, and get the images. And if you do that, then you get a large data set with image text pairing, and you don't need to manually annotate anything. Of course, there's some Google machinery behind that, but this Google machinery already exists anyway, and it was most likely created via all these click rates. So people were looking for images, they were typing in some text, and then they get listed some images, and then in the end, they click on the best ones. And that way, actually, Google was improving their machinery. So you can exploit all this knowledge and create a large data set of image and text. Here's an example for paired video and text. This is a rather noisy one. On YouTube, there are many videos that show you how you can do something. Yeah, for example, you repair a chair that is rusty and so on, and you want to put new paint on it, and then you actually have this YouTube video, and there is some speech that explains what's being done. You can do speech processing, and then you get a corresponding text. This is quite noisy because, first of all, the speech processing is often not perfect, and then often people are just talking of all kinds of stuff that have nothing to do with what you see in the video. Yeah, so they talk of their latest car they bought, and how proud they are of this car, and whatever. And actually, they are painting a chair. Yeah, so of course you then have statistics, and the statistics have to get it right. Yeah, so remove all the noise that has nothing to do with the signal. It makes it a bit harder, but the signal is still there. Yeah, and now you can use actually this image text pairing to learn embeddings that are then good for open world classification. And there are a couple of recent works that do that. Probably the most popular and most simple one is this CLIP approach, where you just have an image encoder and a text encoder. So a normal network. Today, these are all transformers, but you could also use some other architecture. That doesn't matter too much. And then you actually just have a contrastive loss that tells you that for the paired image and text, they should get you to the same point. And if it's a different image and a different text, so that's not part of the pairing, then they should have a low similarity in that space. Yeah, and then you just put a lot of data into that with this loss, and then you learn the text encoder and the image encoder together. Yeah, so then you have a nice embedding where hopefully the information about what is shown in an image maps to the same point as the description of this content in the text. And then you can attest, if you now want to build a classifier without having any class labels, so that's zero-shot classification. It's not completely zero-shot actually, because the information has to come from somewhere. It comes actually from your original training data. But you can now actually build a classifier without class labels by just taking the class names that you are interested in, build a simple sentence from this, for example, the photo of a dog, yeah? And you do that for all the classes you're interested in, and then you're matching the embedding that you get from this text with the embedding from your input image, and then you have an image classifier for these object classes, because the class label that has the highest similarity then to the text embedding, the highest text embedding that has the highest similarity to the image embedding, that has then the class that you see in the image. So this would be open world generalization. And that's what people are also trying with this clip model there. There's also an immediate benefit from these cross-modal tasks that when you have these joint embeddings between images and text, that you can also do text-based video retrieval, for example. Yeah? So you type a text and then you can look for videos that match to this text. Or the other way around, you take a video and you can generate a text, so captioning, that's called captioning, to generate a text for this. Or just the classifier, the zero-shot classifier that I mentioned. There's currently, there are two approaches to that. So one is this clip approach with the large data set at the beginning, where you really learn the text encoder and the image encoder from scratch using all this data. And probably that is actually the best way to do it if you have a lot of data, because then you really learn the embeddings. But of course, many people cannot afford to take 400 million images and just train this model for some while on their machines. And that's why the most common thing that you will see in the literature at the moment is that you use a pre-trained text encoder and a pre-trained image encoder, which already represent the image and the text in a rather good way. And then you only learn a projection network on top. Yeah? So you only learn a small network that then maps the embedding that you already have to an embedding that is compatible with the image embedding. So that way, you have to train much less. You start already with something that is quite reasonable. But the downside of this is that you're restricted to what was already encoded there. Yeah? So, for example, if you have never seen any dog in the image encoder, then it won't be able to actually represent the dog very well, and that is then might be the problem. Okay, if you go with this approach, so you already have a pre-trained image and text encoder, then what most works actually ignore is that in the end you not only want to map the text embedding and the image embedding to the same point for your paired data, but actually you want to also keep the original text and image embedding, because you don't want to have all the nice dogs that you had already in the same place in your image embedding space to be spread out somewhere else. So and the same for the text, and that's why we suggested this cross CLR approach, which tries to avoid it. So you have an additional loss via the negative pairs that ensures that your embedding space that you have in the end stays consistent with the original spaces. The formula looks a little bit large, but it's actually simple. So the green one is the positive pairs, and the red one is the intramodality thing. The intermodality thing, so that's what you usually would have in this cross-modal contrastive learning. Now you just add this orange part, so that also within the negative pairs within the modality should also stay far apart in the final space. And you do that in both directions, of video text and text to video, to make this symmetric, and then you can ensure that your embedding space stays consistent. Another thing that we did here is to avoid false negative pairs when you have influential samples, or that's how we call them. An example for this to motivate it, so you might have a sample with the corresponding text, which is cut tomato and put it in a bowl, and then you have another one, cut tomatoes and mix with the herbs. And now what the contrastive learning tells you is that these two samples should be put apart, because they are different. It's not the same one. That actually hampers the linkage of things that actually should belong together, because both are about tomatoes and even cutting them, which you see actually from the text that they are very similar and they should actually belong together. And also the images actually look a bit similar, so you actually want to put them to the same space. So how can we reduce this effect? And the idea is that we remove so-called influential samples from this negative set. So we don't penalize the embedding space when they are moving towards the same point in the embedding space. And the influence is just measured by the sample connectivity. So if you have a sample that is connected a lot with other samples, then this might be actually one of these samples that connect very well between different instances of a class, and then you don't want to push things apart for these samples. And this turned out to have a positive effect on the learning of the embedding. That's what you see here. So when you compare this cross CLR on the same ground with other contrastive losses from that time, then it performs better than the others. Okay, another quick thing that I want to show is the cooperative hierarchical transformer. So this is an approach that works with videos. And in the spatial domain, we have typically a hierarchy, because all the network architectures actually have some hierarchy. Convolutional networks have them, transformers have them, so you always process the image as a hierarchy. But if you look at the video, there's also a temporal hierarchy. So you can have a look at small snippets of a video, and you can have some long-term content. And currently, there is actually no hierarchy in the models. So they are typically just one big block, and either you don't look at the details locally or you miss the global context. Typically, it's the latter. And with the hierarchical transformer, we actually want, on one hand, that the local embeddings map to the right embedding space, but also the global content maps. Or it's the other way around shown here. So that's the global one. So you have the whole video and a whole paragraph, and you want to map them to the same space, but you also want to map the local parts, so the sentences and the clips to the right embedding space. And if you combine that together, then you can actually capture the long-term content much better. So here's how this architecture looks like. So you have a video branch and a text branch that do the processing there. So these are some transformers that give you some local representation and a global representation. So that is the local one, and here's the global one. Then you can also feed the whole video and the whole paragraph to it. And then you have losses both for the local representation and for the global one. And that ensures that the local representation is consistent and also the global one. And that way you capture both hierarchy levels. Of course, this could be extended if you have more hierarchy levels, but these are the natural ones that you can most easily extract from the data. Now here are some example retrieval results. So if you put a query here, a young person goes snowboarding on a mountain, he goes down, jumps and flips and spins. And then you get here the top 5 videos for that. And that looks quite reasonable. So this video retrieval works based on a text. Also the numbers are good here compared to previous work. Here's an example of text retrieval. Also some success and failure. So the first one for this video sequence, a woman resting next to crushing water. Well, that's not visible here actually. She's smoking a pipe, she blows out a plum of smoke, and that was really the corresponding text example. So here the ranked one was right. Whereas here you have an example where the rank one is also not that bad. A woman stands in front of a crowd of people on a public sidewalk and dances with a male dance partner in ballroom style dance. It's okay, so it looks a little bit like ballroom style. But you see already from the second ranked example, a woman in a leather dress and a hat. Well, there is no hat at all, and also no leather dress. So obviously this model cannot use information that is obviously there to rule out possibilities. Yeah, so this is completely out of the question here, and that's why it gets this wrong. Yeah, the correct one is actually in place 16. Yeah. Also, video retrieval, that's the other way around. So you have a text and then you want to get the most fitting video. Also here it works quite well for these cooking results. Yeah, so melt butter in a pan, so the result is good. And also the other one, melt the butter in a pan, is of course very similar and also works, has also a high score. But here an example that doesn't work well. Slice the bamboo shoots into stripes. And yeah, then you see some chopping of parsley. Yeah, so this is an indication that the model probably didn't see any bamboo shoots, and that's why it didn't know what to do, and it just spits out something. Yeah, so that's again an example of non-working out-of-world, open-world generalization. Yeah, and it's also clear, what would a small kid do that never saw bamboo shoots? Yeah, and then you ask it to find the video where the bamboo shoots are sliced into small pieces. Well, at least it could look for things that are sliced into pieces, and that's also what the model does here. But yeah, it will probably complain and say, I don't know what bamboo shoots are, and that's actually the correct answer here, to say, I don't know what bamboo shoots are, but that's what the machine doesn't do. Yeah, it just produces the result. And the correct one is at place 168. So obviously it doesn't know about bamboo shoots. Okay, and this also shows you that if you want to be successful with these video text models, then you actually need as much data as possible. Yeah? So, and it must be diverse data. Yeah? So the more things you have seen, the better you can filter out the noise and the more things you can cover. Yeah? So that's a success story also of the large companies, that they just use a lot of data. Here's an example of video capturing. It's a very fast video, but for the machine, that's not a big problem. So the ground truth is chopped celery, apple, red grapes, and roasted walnuts, and so on. And then what you get here with these different models, it can be very long. So the MART approach, chop some red onion, there are no onions, there's no garlic. So it just takes what it has seen very often in this context. So kind of similar video, and there they chop garlic, so I just spit out garlic. Garlic is always good for food, so put it in. Yeah, the same for the other model. Yeah, so olive oil and salt was never there, but yeah, it's not bad to use this prior if you don't know what the other thing is. Yeah, so often missing knowledge is covered by just spitting out something that is wrong. Good. So a summary of this video text part. Yeah, so this cross CLR loss, this keeps the consistency with the original embeddings. So that was the reason why it was made. And it avoids false negative pairs via inferential samples. And then this hierarchical transformer links the clip level and the video level embeddings. And the overall summary is now that yeah, the self-supervised learning enables some open world generalization. We're definitely not there yet. It's all not perfect. But it's a direction that is promising. And powerful learning cues come from instance matching. So that you have samples that belong to the same instance, different views of that, and that help you learn the embedding. And this can even lead to class level embeddings via the transitivity between the samples. Yeah, then image text pairing gives you an even more powerful cue, because actually the text is a semantic level information, which you then can map with the raw data from the image, or the same would probably also work for other modalities rather than images. But yeah, well, I'm a computer vision person. That's why I typically use images or videos. Good, that's it. Thank you.
Do you hear me? Yes. So thank you very much for your great talk. Are there questions from the audience? Yes, Peter, let me bring you the microphone.
Yes, thanks for this very nice talk. These scores that are reported on the last few slides, I mean, it would also be really nice if the method reports how certain it is about the score.
Yeah, there are of course some probabilistic deep learning approaches that also try to give a certainty. There are also a lot of works on calibration of models. You can improve on that, but if you run out of distribution, then often you're lost. So the best it can do is actually find out that it runs out of distribution, and there are a couple of approaches that do that. For example, a very simple approach is some nearest neighbor matching to the training data. Yeah? So if you know that you're far away from a training sample, then there's a good indication that something is wrong, but this is of course also not very efficient because then you have to match to the whole training set. If that is large, then that's a problem. But there are also some other approaches. Yeah, so there is some research in that direction.
Maybe I could ask the next question. Yeah, sure. So I would say most of your talk was focused on better strategies to learn representations which could generalize, right? My question is, how much do you think different architectures would be influential in learning better representation? So in the past years, I would say we see like a rise in using transformers, well, mostly in language domain, but for example, do you see it the case that, I don't know, transformers also overtake convolutional neural networks in vision fields, or?
I think they did already, although not by much. Yeah, so there is one thing in the transformer that is quite useful, that is this matching of tokens within the image. So that way you can actually do some clustering within the image, which a convolutional network cannot do. It can only do a clustering internally via the template itself that it learns. But that's then the template that it matches, and the transformer has this additional possibility that it can match within the image. So that's definitely an advantage of the transformer, and that is probably the reason why, yeah, if you now put a bit more effort into it, convolutional networks have been tuned a lot, that you could get a small benefit out of that, especially when you think about self-supervised learning. I think for supervised learning, it doesn't make a big difference. But for self-supervised learning, where clustering plays a larger role, there this advantage of the transformer might be relevant.
Thank you. Are there more questions from the audience here? Audience online, if you have questions, please go on or write in the chat. Yeah, so
probably someone has to read the chat.
I think these are before.
Okay.
No more questions?
Seems calm audience. Yeah.
I mean, you make this very important point that when you run out of distribution, you're lost. And of course, if the dimension of the data is, so if you have small dimensions, if you have fewer dimensions, then it's not so easy to run out of distribution, right?
Yeah.
So would that also be a strategy to not get lost in some cases?
Yeah, on the other hand, deep learning has benefited actually from the high dimensions.
Yeah.
So the whole thing only started to work when dimensionality went up. So I think that, and also if you have, even on a 1D space, you can run out of distribution if all your training samples are here and then you have a sample far away. So I think the dimensionality reduction can, I don't think it's a strategy to help on that problem. It's more that you already need the learning signals that cover the whole space, or at least the whole manifold in which data could be, and yeah, having labeled data is actually kind of the worst way to establish that, because then you really specify everything for that labeled data, but you you are not good on the other parts of the space. That might also exist, yeah. Well,
good. So maybe one final question. So I would say, based on what you presented, it seems that vision and language are really playing with each other and getting better together. Do you see the same thing maybe with robotics and vision in the future?
Yeah, robotics and vision, these are natural counterparts. It's just that vision and language, we have lots of working examples. In robotics, we actually have something, well, you buy a vacuum cleaner robot to see a robot who works. And even that one, you have to make sure that it doesn't get trapped in a simple cable or so. So I think in robotics, there's so much more to do. So I think, yeah, that is like, if you're looking for open problems, then robotics is best, I would say. And of course, vision and robotics goes very well together because that's one of the sensing modalities that is probably most important for the robot. And not the only one, but many. But in robotics, the additional big problem that cannot be solved by AI is actually the mechanics. And that is also very important. So often robots fail just because of the mechanics and not because they are too stupid. So yeah, you probably need someone who's good in mechanics, and then you have to couple them with a good AI person. And then if they work together, then you get a good robot. Yeah, there's a lot of tool in this field. I like that very much. Embodied learning is also a term for that. And also many of the self-supervised cues that you can generate, they can actually come from robotics because you're doing something and you see the result and then you can adapt. So that's a very good self-supervised learning cue. Yeah, but it comes with much more work. So that's not a 3-year project, but more a 20-year project, I'd say.
Thank you very much. Final call. Is there any questions? Well, if not, then